Okay, so I want to use the technical lemma from the previous video to show kind of another sort of Cauchy integrability condition for bounded functions. So the theorem is the following. The theorem says if f is bounded, let's say if f is bounded, then f is integrable if and only if for all epsilon greater than 0, there exists a delta such that whenever we have a partition whose mesh size is less than delta, then we have this typical sort of Cauchy condition, u of fp minus L of fp is less than epsilon. Okay, so the proof of this, it's an if and only if statement. So there's two directions. One direction is easy. So from 2 videos ago, we saw that a function is integrable if and only if there exists one partition such that u of fp minus L of fp is less than epsilon. That means then the function is integrable if and only if there exists a partition p such that u of fp minus L of fp is less than epsilon. Okay, well, what this says is if for all epsilon, there exists a delta such that for any partition whose mesh size is less than delta, then this holds. So in other words, it's not just that there's one, the statement of the theorem says there isn't just one partition that satisfies u of fp minus L of fp is less than epsilon. Any partition whose mesh size is less than delta satisfies this condition. So if the epsilon delta condition holds, in the statement of the theorem. So if the epsilon delta condition holds, then the function is integrable. So the hard part of this theorem, the hard part of the proof is to show that if f is integrable, then for all epsilon greater than 0, there exists a delta such that if the mesh size is less than delta, then this holds. So in other words, the hard part is proving if f is integrable, then the epsilon delta condition holds. So let's assume f is integrable. Assume f is integrable. And let epsilon be greater than 0. Okay, so since f is integrable, the one thing that we do know, this is going to be kind of like a bootstrapping argument. The one thing that we do know is there exists a partition p naught such that u of f p naught minus L of f p naught is less than epsilon. And what we're actually going to show, let me erase this and write this again because I want to be clear about what we're going to show. We're going to show that there exists a delta such that we're going to show that there exists a delta such that if the mesh of p is less than delta, we're actually going to show then that u of fp minus L of fp is less than 5 epsilon. Okay, and this of course implies the statement that u of fp minus this implies that for all epsilon greater than 0, we can find a delta such that u of fp minus L of fp is less than epsilon. Okay, we've been doing similar things in this class. Okay, so to prove that, we know since f is integrable, there is a p naught with u of f p0 minus L of f p0 is less than epsilon. Okay, and let m, we're going to define a few things. Let m be equal to the number of points. So just the number of subintervals, if you want to think about it, in p naught. And then a is going to be the bound on the absolute value of x. We know f is bounded, so we're going to say f of x is less than or equal to a. And now I have to tell you what my delta is. So given an epsilon, delta is going to be equal to epsilon over m times A. Okay, so now I'm going to let P be any partition with the mesh of P less than this prescribed delta. Okay, so I'm going to now define Q to be a refinement of P. In particular, P is going to be P union P naught. And what we're going to do, we're going to say, okay, well, Q is a refinement of P naught. So the epsilon inequality for P naught is also going to hold for Q. Now we're going to say, okay, I'm going to use a previous technical lemma, the technical lemma from the previous video, to say, all right, well, I know that I can control the difference between L of Q and L of P. And now, since the inequality, the epsilon inequality holds for Q, I'm also going to show that it holds for P as well. And I'm going to do that with the following. I'm going to do that in part by using the following inequality. I want to look at L of FQ minus L of FP. Okay, so let's think about this. Q is a refinement of P. So I know L of FQ is going to be, greater than L of FP, but I want to control how much greater it's going to be. And I'm going to use the previous technical lemma. So what is the difference between Q and P? Well, I've just added in all of the points from P naught. Now, if I think about adding just one at a time, adding a point, I take P and just one at a time, I add a point from P naught to P. Well, every time I do that, I know that this difference is going to be the difference is going to be less than or equal to 2A delta. And I'm going to do this m times. So if I apply the previous, and I know this fact here that I just wrote from the previous technical lemma. This isn't exactly correct yet. This is what happens if I just add 1 point from P naught to P. Okay, I know that this inequality is going to be less than or equal to 2A delta. But I'm doing this, there are m elements in P naught. So I'm going to do this m times. I'm going to apply the technical lemma m times. And so this is actually an m there. But I'm going to have my m, my 2A. Notice delta is equal to epsilon over A times m. So overall, this is just equal to 2 epsilon. And similarly, I know that U of FP minus U of FQ is going to be less than or equal to 2 epsilon. Okay, so now I'm going to prove what I want to prove about U of FP and L of FP. So I know that U of FP, by this inequality here, is less than or equal to U of FQ plus 2 epsilon. I know Q is a refinement of P naught, so this is less than or equal to U of F P naught plus 2 epsilon. I know P naught satisfies the Cauchy condition, so this U of F P naught is less than or equal to L of F P naught plus epsilon. I have a 2 epsilon, so this will be plus 3 epsilon. Okay, I know L of P naught, again, Q is a refinement of P, so L of P naught is less than or equal to L of FQ, and carry through the plus 3 epsilon. And now I'm going to use the top inequality here to show that L of FQ is less than or equal to L of FP plus 2 epsilon, plus I have my 3 epsilon, so in total, plus 5 epsilon. And actually, at some point, actually, these inequalities are less than here, not less than or equal to. So this one is less than, and that one's less than. At any rate, U of FP is less than L of FP plus 5 epsilon, which is what I said I was going to show. So that proves this theorem. It proves that F is integrable. If F is bounded, F is integrable if and only if for all epsilon greater than 0, there exists a delta such that if the mesh size of P is less than delta, then U of FP minus L of FP is less than epsilon.